Well, it turns out that babies grow up with new things. Like, I don't know how young they can get the computer. I mean, how young they can get the phone. That's a fight between them and parents. I'm watching that fight. I have a grandson who is 1. So his mother is addicted to phones, and we'll see. But I expect at least at 5 that they should have their phones. When they come home here, they play with these computers and ruin my computers. Okay. Now, the link to the drive. I'll give you the link to the drive. It's right here. Here. And yes, you want to learn quantum computing. Okay, cool. For that, I need to do just one thing. I stop sharing. I share again. But now that I'm clicking on share sound so that I will hear and you will hear whatever I want to present. So now we can listen to this book. The book is by this guy, Chris Ferry, who writes other books of a similar nature. And somebody reads this book here. So let's just, it's 1 minute, 30 seconds.
Quantum computing for babies. This is a ball. It can be red or blue. It is 1 bit of information. 8 bits make a byte. Many bytes make data. Data lives in a computer. Computers are useful. They solve problems. Problems are solved by changing data. Some problems are easy and some problems are hard. Some problems are too hard for a computer using bits. But wait!
By the way, you noticed what they introduced. They said, here's 6. Can you break it down into prime factors? And they broke it down into 2 times 3. But this is a large number. Can you break that number into prime factors? That's what they're doing here.
What is this down here? It's a quantum bit, a qubit. It can be red or blue or anything at all.
Right, and you notice what they've done. They introduced the major concept of quantum bit, and they introduced it as a quantum bit can be anything at all.
Many qubits make quantum data. Quantum data lives in a quantum computer. Data can be copied. Quantum data cannot be copied.
That's an important principle in quantum computing, that you cannot duplicate a quantum bit. It's not allowed by physics. You can only give that same bit to another person. What that means, we will see later. But they are introducing the major concepts of quantum computing.
We can watch a computer at work, but we cannot watch a quantum computer at work.
But we cannot watch quantum computer at work. Well, that really is also one of the deep concepts in quantum computing, and is that you have to leave it alone. You're not allowed to see how it performs the computation because that will break everything. Now, that's not exactly true in the sense that you can look at it from the outside, and I'll show you the picture, but you cannot look at it inside. Quickly looking at something. Okay, you're very happy. I think, Arge, you're playing a baby, and you are very happy baby. So let's continue.
Work. We can only see the answer it gives. So why do we want a quantum computer? Because quantum computers can solve hard problems. Now you know quantum computing.
Okay, I think it is a wonderful book. And you can buy these books as presents to your children. But the major idea, of course, is that babies grow up with phones and they're not surprised by them. So this gay baby will grow with quantum computers and will not be surprised when they see them. Now, before we go here, I want to tell you my personal story was that I still could not decide that does quantum computing exist or is it some kind of hype? What convinced me was not that my nephew is building them, but the fact that it costs $2 a second. It must be worth something if people are paying that much. Now, what I will show you, our labs, they will all be emulators, but they guarantee them that they will be precise emulators. Okay, but price. So we just say price of quantum computing. $1.49, $1.50, but it's not the same. It's the right price, but not for the right thing. Let's find IBM. Okay, price of quantum computing time. And maybe I should say cost. Now that's to build it, but to use it, I'm sorry, but that's what you would have to go through anyway. IBM. In the cloud, in the IBM cloud, that's where you get it. You probably already found it. But that is the answer. Processors, modern processors, Falcon R5, and they come at $1.60 per Qiskit runtime. Pronounced Qiskit. So that is the quantum computer. Now, if we want to see a quantum computer, of course, we know what to do. We search for quantum computer and we look in the images. And that's a picture of a quantum computer. Any of these will do. So they really do exist. And the latest and greatest and biggest quantum computing that was announced by IBM has 1,432 qubits. Now, what is a qubit? I'll show you what it is. It's an analogy to bit. And so essentially, you're back to the world of extremely primitive and rudimentary computers, like very first computers, which were judged by how much memory they have. So these are judged by 1,433 qubits. Let's go back to the slides. No, not yet. That's a little early. So why would you want them? Because obviously that's very big step back. And I will tell you right away. Yes, you take the current computers and you say, okay, no compiler and no language and no addition even, no arithmetic, but instead you're only allowed to have logics. For example, if you want to program A plus B, and one of the labs shows how to do 1 plus 1, it will be 2. So you have to reprogram it based on logic gates. Now, logic gates is something you might be familiar. That is studied in the very beginning of electrical engineering, let's say, course. And if so, the answer is that you have to build a scheme. You have to build every quantum computer from scratch. Yes, I agree, QC is not hype, but it cannot do anything Jim says yet. So it is not a general computer in the sense that you cannot program to solve your, let's say, tax problem, but you can build a special network, a special logical combination of logical gates that will solve a specific problem. So you cannot solve all the problems that you could potentially want, but only some. Now, why would you want it at all? Just because of speed. You can solve huge problems. You can take over, let's say, blockchain. You can completely kill SSH. That site says it's secure. But why does it say it's secure? Because there is encryption going on in our communication where it can easily break that encryption. Now, are we in danger? No. If you search for how big does the computer have to be, it has to have probably 1 million bits, 1 million. So you would think it's a lot, but on the other hand, IBM had 5 qubits in their computer just maybe a year or two ago, and now we have 1,000. So potentially in a year or two, they will have 1 million, and then everybody's in danger. Now, people are preparing for that. And for example, one of the kings of the, let's say, encryption and other things are the makers of Terraform. And the makers of Terraform are HashiCorp. So they have a blog here. I don't see the blog, but they have it here. And they will tell you what are they preparing for the day when the encryption will all be broken. So people do take it seriously. So why learn about it today, and why learn about it at all? Well, that's because this time when it will have 1 million computers, probably not that far away. And therefore, it is okay to prepare it now. It is used commercially. That's what IBM is mostly working toward. Now, I'll chat a little more, but then I'll show you the real lab, and then we'll see what it is. Now, that is a link to this thing. So it is just the beginning of this cartoon, but it turns out it is from Quora, and it is an attempt by many brilliant people to explain to the lay person what is quantum computing. So the mother comes in and she says the child reading. Obviously, she got him, and she's very unhappy. You can see that he's reading, but what is he reading? Quantum computing. Okay, so obviously it is a play of parents talk to the children, but they talk about quantum computing, and they play here on all the innuendos that you could have. So let's go. That's the talk. That's the one, and they start talking. But the end is that the boy comes with he knows what those elementary particles do when nobody's watching. Okay, you can laugh at it at your leisure, but I'll tell you that they do touch on every important point in quantum computing. Yes, it fed not 5,000 qubits, but 5 qubits. I believe that's true. Okay, so let's continue. And let's talk about, they will tell you, you know, what is a bit? That's what the computers are made of. What is a qubit? That is a bit that is represented by, let's say, an electron. The truth is that they can build quantum computers on a few different foundations. And I believe that the IBM quantum computers are built on superconducting elements that control those electrons. Okay, the electron, as we know from physics, can be pointing up in its spin, or it can be pointing down in its spin. Therefore, it will have represent 1 or 0. Okay, so it represents 1 or 0, and all was good until this experiment when they saw something strange. I'll explain this experiment in a short while, but if you say that your electron, or a photon in this case, your photon represents either 1 facing up or 0 facing down, then it goes through a slit and you can measure what it represents. It's either 1 or 0. What they found in 1800, that's how long ago, they found that if you make less and less photons go, then you would expect 1 slit for all the photons that go through that, and 1 bar, and then another bar would be for all the photons that go there, and that's another bar, and that's your way of measuring. That's how you measure, is it up or down? What they found out is that when there's a lot of light, then of course there's interference. That's normal. But you expect that when you have less and less light, there is no interference. But there was, which means that, and the children today will get it very easy. By the way, there is another book on quantum computing for babies. It's called Entanglement for Babies, and it's talking about this. But that was a problem that bothered the physicists for the next 200 years. And they said, well, simple, this photon, it is both a particle and a wave. And sometimes when you don't watch, then it's a wave. When you do watch, that's a particle. Now, that sounds like science fiction, but it makes sense in the sense that, okay, it decides to behave as a wave when you do watch, and it decides to behave as a particle when you don't watch, but it was hard to stomach. So there are a few theories. We are not going to go into theories, however. We'll just say that if these photons can act as waves, if you don't watch them, give them some problem to solve. And when you don't watch them, they will solve that problem, and then you will ask to present the result. Okay, so you don't watch them, and if you don't watch them, they can interact much faster than our bits on the electronic computer. Our bits are doing everything sequentially, but the waves interfere all the time, and therefore you can get much faster computation. How much faster? Well, however many bits. If you have 30 qubits, then all 30 talk to each other. And therefore, you get 2 to the power of 30 combinations. If you have 1,000, you have 2 to the power of 1,000. Well, practically 2 to the power of 30 is enough. Enough in the sense that that is where you cannot emulate it anymore. So all our emulations, they will be limited to something that's less than 30 qubits, because if it was more, then our emulators would break. That's enough. That gives rise to interesting theories about Shiva dancing with each photon, but obviously you will be thought as a loony, and therefore we are not going to go there. But this will be the practical reasons why you would want to learn about quantum computing, what practical applications you would expect, and then the lab, as I promised. So, first law is that our computers are limited in speed. The number of transistors used to double, but that broke in about 2012. It didn't work anymore, and we couldn't get any faster, because if you make smaller computers, they generate so much heat that they burn. Therefore, there is a need for some very quick computation, and quantum computing does it. Another fact is that, as I mentioned, the quantum computer can factor prime numbers, and it can do this fast. All of our unhackable encryption is based on the fact that it's very hard to break large numbers into prime components, and therefore our normal computers cannot do it. It would take it 10,000 years to hack one combination, but if all the computers, their bits of quantum computers work all together, then you will get an answer. Now, that is only one algorithm. In other words, that's only one problem. What I'm saying now is that using quantum computer, you cannot have general algorithms. You can have only one specific algorithm and only that one which solves one problem, finding the prime dividers of a big number. Other problems, well, each problem, each algorithm is worth a Nobel Prize, or at least it's a major invention. The algorithm that is good for quantum computers and that does this, that divides large numbers into primes, was invented by a professor by the name of Shor. So let's go, I think Peter Shor, quantum computing. That's him. And as the commentary said, and it's talking about breaking the internet, but not yet. It mentioned that yes, these are all people who are alive. This is in the making, and he invented the first algorithm ever that worked on quantum computer. So the commentator said that he looks exactly like a professor who invents algorithms. That's him. So the point of that is that each program that does anything serious written for the quantum computer is a major breakthrough, a major invention. So there are about 12, 15 known algorithms that work on quantum computers right now. Another thing that is very good for quantum computing, but honestly, nothing works as yet, is finding optimal routes for delivery. Because very often there is no algorithm, no formula, and you have to go through all the combinations. Well, and what is better for going through all the combinations if not quantum computing? That's another reason. Another reason is that it actual physical, I'll show you, exists. You can do it, and you can set it into a simulation mode, emulation mode, and it will run it for you on your computer on the IBM. Or you can say, okay, I accept $1.60 cents per second, and please run it on IBM quantum computer. We can do it now. Okay, then here we have a list of possible applications of quantum computing. I'm not going to read that list. You can have the slides. Besides, really, you would have to investigate each individual area and see for yourself, is it real or is it not? Most of them, they will say, it kind of works, but we're waiting for a bigger computer. Now, I want to check what you guys are saying. For example, Jim, a traveling salesman problem, except that I believe that traveling salesman problem has a solution. It's dynamic programming. But one of the optimization problems that doesn't have a solution is the how do I cut a particular piece of cloth so that I can use it in many different ways. There are some programs that are too hard, too large, and you need to go through all the combinations. So far, breaking a number into primes is still the best example. Okay, now that is the story, but that story tells you about what is quantum. By the way, here we have the best possible textbook for quantum computing. It's not the easiest. There is no easy textbook. I can tell you for sure because I tried every one. I read every book on Amazon. I took every course, and I will say personally that I like the Qiskit from IBM the best. It goes, explains, and you get lost in a certain point of time, but it shows you, and I will show you how to do it. And it says that quantum computing, people right away start talking about the classical computer, and they talk about that they have bits, but here you have qubits, and as opposed to regular bit, which is really is either 0 or 1. Qubits, if you don't measure them, they are anything. And if they're anything, then just don't measure, but they can do the work. Okay, and that here explains how they're anything, and they go toss the coin. But if you randomly toss coins, that will be more or less 50-50. But then if you toss the quantum coins down below here, then they will be strange, and that strangeness physicists don't explain as yet. But what will happen is they get stuck. Now here they don't. Let's go to the quantum coins. I skip because I don't find that it's really illuminating. But you toss a quantum coin, and what you see, not here, maybe here. No. You see an amazing thing that quantum coins break all the laws. They break all the laws of probabilities too, and you keep tossing them and they come up on the same side and they talk to each other. The end result is that you need to come up with negative probabilities. So that is not the greatest possible explanation, and that's why I only mention it. But I would say don't spend much time on it because it comes with this -2 probability. So when you describe your coin, you have to describe it as a vector that can have unusual values. So the only reason you'll talk about this is because it's fast. Okay, so here we are on our slide, and these are the labs. Now, I'll walk you through these labs. I'll show you how they work, and that will be real. That's how you work with quantum computing. So let's switch to that. Here is what I need to verify. Okay, it seems that we're okay. Here is the lab, and it is mentioned. Let's close all of that. And here on Webinar Run, we have the labs. So far it is open. So if you click there, you will see the labs. I'm giving you the link to the labs, Quantum Labs, putting it on the chat here. Okay, you know, a lot of math. You could do the 4-column mapping theorem. Yes. Okay, that's all the labs. From now on, I'll be opening this link and going to this lab. And what it says is I will walk through this. This is the setup. There are 3 steps in the setup, and it uses Python. But it uses Python in a special way. So I'll show you exactly what you need to do. Now, we are only doing a first webinar. We might think of doing a whole series of webinars. I think it would make sense. So we will limit to what we can reasonably do. The first thing that you do is set up your Python. Okay. The recommended way, the one that I would say is a good way, is installing Conda. Anaconda, and if you do this, then you will have the Conda at your disposal right here. I'll make it bigger, okay? And I will say Conda as a command to verify that exists. Okay, it's a way to talk to all the installers, and I can say Conda deactivate, which means just get out of Conda whatever it is and stop. Now, virtual environments in Python are a very simple way to have a completely different environment for each problem. You just say Conda activate, or in this lab, you would first create it and then activate, but you say activate the environment that I created. Yeah, activate I meant. Okay, now I'm in Qiskit. In other words, whatever I install for that will not affect my computer. It will only stay here. That's kind of a virtual environment. And that's what it's called, VM. So I'm here. The next thing that you need to do, and that's all described in the labs, how you do it. But we say that you first install Anaconda. Of course, you can do something else, but I know that that works. So you do this. The next step is you install the library. Let's look at what you need to install. You need to install, first of all, create a new environment called Qiskit, or just activate this. I already did that. Then install library called Qiskit. That is IBM library that imitates or really works with the quantum computers. Now we're getting real. So I can do this, but because I already did it, all that will happen now. I think I should close those slides. They're always in the way. Okay. So here I can say install Qiskit, but it will check everyone and will just verify that they are there. I'm only showing it to be consistent and sequentially install all of that. The next thing that you do is you install a separate library called visualization. And that is because the graphs that you will see are a little bit different from all the other normal graphs. Okay, but again, it's already here. I'm only checking that it's installed. And even for machine learning, you would install for machine learning. Now I'm doing this because it verifies everything for today. And okay, and it feels real. What you can do is this. You can run Python on your machine exactly the way it says here. You can find another virtual machine. Essentially, that's all you have to do. So I'm showing it quick, but that you will be able to do after class on your own and tell me about how it worked for you. So that is an install of first Python with Conda, and then Qiskit library, and then you will be using Notebook. We will be running Jupyter Notebook again. That's something very easy. You can look it up, but you verify that you have this IP kernel installed. So let's verify that we do. As you see, it does. And then you install additional textbook. That's theirs. That's nothing to do with the deep libraries, but it's the Qiskit textbook from IBM. So you install that. And it's not cloning anything really, it's just installing the necessary libraries. And we can run all of our quantum computing there. After that, you do Jupyter Lab. Jupyter Lab is the way to start your notebooks in the browser. Now, where am I? Right now, I am in quantum computing lab. It's these same labs that I'm showing you. I'm going through this. So you can clone this because that's already there, or you can just go through each lab, copy and paste. We're going to do the first one here. Well, the second one. That's what we're going to do. Okay. Now, in my case, if I say Jupyter, Jupyter U lab, then it should start a server, a web server, and show me the content of this directory. Okay, that's what it does. And it's already opened on this 1, but no, that's not what I want. So how do you navigate in Jupyter? You go up like this, and you go back here, and you open this one. Now, for the lack of time, and because it is the first time, I'll just go through that, and I briefly show you what it does and briefly explain, and then we will have some time for questions. Okay, so what we're doing is writing a real quantum computing program. And as I told you, the real quantum computing program is not written in any language. We're down from the compiler level, assembly, we're down, we don't have even arithmetics, but instead all we have is go back to the level of logical circuits. That is what is implemented by quantum computers. Okay, so with that preface, we can see what we're going to do. We're going to build our own computer. We're going to build it, and we're going to show the circuit. And with that circuit, we're going to implement something interesting because we will use the simulator. Now, this lab, I kept it, is already executed. So first, I will go and show you what you should expect, and then I'll go and show you that it really does that. So here, we are creating a little computer with 8, I believe, yes, with 8 qubits. And what can you do with those qubits? You can let them play, you can let them do their work, and then you can measure them and get the answer. This is the answer. The answer is real bits. So if I'm looking for a certain number that will be the result of my calculations, then I'm letting the qubits do the work. And finally, in the end, I'm copying them into the real bit situation. That will be my answer. So that's why sometimes they just say quantum circuit of 8 qubits. And sometimes they say 8 because usually the number of regular bits is the same as a qubit. It's kind of output or print for you. So that's what you create. And then you're going to say, okay, right now I'm using a simulator. So they promise that whatever you do will work as a simulator, exactly the same as a real quantum computer, but it will only work up until about 30, as I told you. So we will be counting just the number of bits. That's what we're counting. And we are encoding the input. We are setting these qubits to something previously known. I'm giving the input, so to say. I'm setting the qubit number 1, that's the second qubit. This is the first, that's the second. And I'm setting qubit number 5, and that's here. So I gave it a number as an input, and that number is 2 plus, let's say, that would be 1, that would be 2, 4, 8, 16, 32. So 2 plus 32, 24. Then you're asking it to show you what you see, and then you're measuring. Measure means set these bits that would correspond to non-zero bit in this. That's what will happen when you measure. And that here is already going too far. That's creating another qubit, another circuit with more qubits, and a more complicated logical gate. What is a logical gate? I already told you. It's those same gates that you had when you were studying computers on a very, very basic level, except that they are using a special notation for the XOR gate, because essentially it's the gate that will convert 0, 0 to 0, 1, 1 to 0, 1, 1, 1, 0, and 0, 1 to 1, plus It has to be even more basic than the initial gate, and it needs to have one input and one control qubit. So they invented that idea today. A guy by the name of Toffoli invented it, and that's why it's called the Toffoli gate. So not going too far, we then verify what versions of we software we run. What I'm suggesting is that we restart kernel, clear all output, okay, and verify how it works. Now, the way to run it is either by clicking run here, there you are, and it imports now the necessary libraries, which include quantum circuit, assemble, and air, and this air is a simulator, or you can shift return. That's how you work with those guys. So right now I shift return because I didn't want to mouse over to here. Then you can measure the circuit and see what it looks like. Now it looks somewhat different. It does the same thing. It's 8 qubits here, but it looks somewhat different because I'm on a Mac, and the one that I saved was on a Ubuntu, so it looks a little bit different, but means the same thing. So now we're running the simulator. And now I'm setting the qubits, the second and the sixth, and I want to measure them all. In other words, I want to set the output. Then I'm using the gate. I'm using the CX. Now X is not, CX is, it's a gate of 2 qubits combined with a NOT. And I think that's enough for now, because I also want to get your reactions on that. What we can say about quantum computing from this introduction. I will stop share. Stop share. And I think everybody's amazed by what this quantum computing is. So you can chat or you can talk. I will also allow everybody to talk.
So how does this relate to, let's say, black masks or a billion groups? Because I know there's math behind it, like
Yes, but the most basic thing is that all these bits, they work together. So if one bit can be in only yes or no or 0, 1 state, that means 2 possibilities. The other qubit can also be yes or no, so that's 2 times 2 possibilities. And the next bit, qubit number 3, can also be in the 1 or 0, yes or no. That's times 2, and that's 8. And you see the formula, it's 2 to the power of number of bits. Now, the only trick of quantum computing is that they can do these calculations all the time, non-stop, when you are not looking. So you get as many, you get the speed as much faster as you have the number of bits. So for example, with the latest computer, 1,433 bits, it's about 2 to the 1,000.
I think the speed is due to entanglement, really, because a single qubit isn't necessarily faster than a bit like an electron, but due to entanglement, several of them flip at the same time. That's where the speed comes from. So the thing what I think I saw here in the lab, right? We technically had 2 qubit apps. One was encode and the other one was measure. Did we have any other qubit apps in the lab? Because I know there are qubit operations in these things. We just have the two, the encode and the measure.
Well, you're saying that the speed up is essential because of the entanglement, and that is something that we didn't even talk about. So first of all, if you go to YouTube and you look for entanglement, quantum entanglement for babies, you will find a book about that. So skipping this for now, we'll talk about that entanglement is a way for two qubits to communicate, violating all known laws, including the law of physics. I mean, the speed of light is the biggest number you can get, but they can communicate at any distance. And nobody really knows if that's really how you should explain it, or there is another paradox. And that's what I'm trying to avoid. Paradoxes for late night conversations, right? But there is another thing that we haven't talked about, and that's how you build those computers, how you use entanglement. But the end result is yet you get very fast computers. And I believe that I see the absolute need to continue. So every Thursday becomes the quantum computing Thursday.
Very cool. So we do see two operations, right? We make a quantum circuit, we do initialize, well, there is a symbol, and then we have somewhere a measure. Not a measure.
Hello.
Yes, I'm clicking on allow everybody to talk because everybody wants to join in the conversation. Now you're also allowed to chat if you want. I'm also thinking about, yes.
Yes, can you repeat, please?
Excuse me?
Were you talking to me?
I was talking to everybody trying to get their output or input. What I'm suggesting is that really let's go slow, and that was an introduction. Let's do labs. Let's explain every cell in this lab. Let's see what it does. But the final goal, let me show you the final goal, is the final goal is to cover this. And when I say cover this, then what we need is documentation home. And as you can see, it allows you to go into the quantum computing, including the simple things, but in the end, it promises every algorithm that there is in, well, the tutorial. Every algorithm that there is, and well, that's the plan. I think it's okay that other people are doing it on their own. It's okay that they are having summer schools and they're having textbooks complete and available. And you saw as I was going different courses, but I went through all of them and I didn't find anyone that extremely easy and good, except for the actual IBM Qiskit. So I plan to try to go slowly through every step, making it available and accessible. Oh, and I was not sharing when I was talking about this. But that's where I was going. So going through most of that. And even those guys made it quite hard. Maybe because the subject itself is a little bit hard, and the best illustration is found in our slides. The best illustration was this. Okay, so it may have been a fun cartoon, but if you go there, you will see that a couple dozen brilliant people try to answer one simple question. What is an intuitive explanation of quantum computing? And nobody succeeded completely. So gradually, after you learn a bit more, you will finally get your own intuitive explanation of quantum computing. But judging by this, there was none, because they keep going with this. And in fact, every now and then there is a new entry and a new attempt to do this. So I think what I should do is really give you that link, which puts it all in perspective. Here you are. I'm putting this on the webinar run. And also giving it to you on chat. So I think it's good enough. I don't want to establish a Slack or anything like that. I think even if you come once a week for an hour, that's already a lot. And even though there is a way to join the Slack of Quizzkit and see all the experts there, I'm not replicating that, because if you want, you'll join that other Slack. Okay, guys, so it was a big pleasure. I wish you a good weekend, and I hope to see you the next Thursday. Thank you, Jim. Thank you, Leon, Lawrence, John, Eva. Okay, thank you, Shane, Jane, Jose. Okay, thank you, everybody.